Well, hello scrappers, and welcome back to my channel. Okay, so a while back I released some videos about melting down the cement copper I get out of my waste bucket when I'm processing IC chips to recover gold from them, gold and silver. You know, all of the waste liquids go through my stock pot and then they go into my waste bucket. And in the waste bucket, a lot of copper, cement copper accumulates. And I've been casting bars out of them. They're impure. They have impurities in them. And some of those impurities are precious metals, like gold, silver, whatnot. So, in another video, I had built a little electrolytic cell and was refining the copper, one of my copper bars, in that electrolytic cell. It was just a little cell, experimental cell, built in a beaker. And I managed to plate a lot of copper from one of my bars off onto a copper wire grid and accumulate a lot of gunk in the bottom of the beaker called anode slimes, which are the impurities, because only the copper plates out. Everything else in here that's not copper winds up on the bottom of the electrolytic cell. It's called anode slimes. And everything that winds up down there, including the precious metals that are in here. And I was able to recover some gold from those anode slimes. It's just a small amount, but I only had a small amount of anode slimes to work with for my little prototype cell. So I got to thinking, I need to scale up because I've got a lot of copper. And you know, if I process all the copper from my waste bucket, I should be able to get a decent amount of precious metals out of it. So I decided to scale up. This is my new electrolytic cell. Right here. Yeah. Okay, I will explain this in a little more detail. This one has 1, 2, 3, 4 of my copper bar anodes, and it's got 3 wire grid cathodes. And I just made these cathodes just by bending wire together like that. So what's going to happen is the copper bars are going to be electrically connected to the positive rail, or the anode, and the copper wire grid cathodes will be connected to the negative rail. So I'll connect this side to a power supply, positive side of the power supply. I'll connect this side to the negative side. As you can see, I've got some little rubber hose insulators on there, so they're only sitting on one rail or the other. And all of the copper bars are sitting on the positive rail, and all of the copper cathodes are sitting on the negative rail, and they're insulated from the opposite rail. I 3D printed all of the plastic parts in here, the plastic legs, the plastic spacers. I 3D printed all that stuff, and it's just sitting in a Rubbermaid tub here. So what I need to do is I need to get a power supply that will power this. And we'll talk a little bit about power supplies in a little bit. And I need to fill this with an electrolyte. Now there's a couple different electrolytes I could use. I could use copper sulfate, which is commonly what's used for copper electrolysis. Or I could use copper nitrate, which I happen to have a lot of on hand because it's a byproduct of me processing the IC chips and getting the gold out of them. I have a lot of copper nitrate on hand. So I will use copper nitrate as an electrolyte in here, just like I did in my little prototype cell that worked in a beaker. So what's going to happen here is after I fill this up with copper nitrate electrolyte and I put power to it, the copper anodes, the copper bars here, will slowly dissolve into solution, dropping anything that is not copper to the bottom of the bin, including all those lovely precious metals. And the copper in solution will plate out on the cathodes, and they should get fatter and fatter and fatter over time as the anodes get skinnier and skinnier and skinnier over time. And we should accumulate a lot of anode slimes, which will have the precious metals in them, which I can process. So that's the idea. Now this is an experiment. Now this has worked on the small scale. We'll have to see if it'll work on the big scale. And in the tradition of the Mythbusters, you know, they say, I have a saying on the Mythbusters, and I heard it, I was a big Mythbusters fan, and I don't know how many times I heard him say it. You know, the difference between science and just screwing around is writing it down. So we're going to collect some data. I'm going to weigh up the anodes and the cathodes, and we'll see how much weight the anodes lose, how much weight the cathodes gain, and we'll keep track of how much current we're putting through the cell, because the amount of copper that's moved should be directly proportional to the amount of amperage that the cell's running at. So I'm going to need a power supply that can provide a lot of amps too, so we'll get a look at that in a second. So let me get the scale out though. We'll weigh up some things and see what our initial conditions are, and after the cell runs for a while, we'll weigh them again and see how things are going. So here's a little closer view of one of the anodes and one of the cathodes. Now the anode is just one of my rough cast ingots of copper that I melted and cast, and you can see the other video how I did that. And what I did was I drilled and tapped a 1024 hole in the top of it there, and I have inserted a brass screw and washer and some heavy-duty copper wire. I think this is 8-gauge copper wire that I used to make the hanger, for lack of a better term. There's probably an industry term in the plating industry for what this is. But this is a hanger for hanging it in the cell. This side's going to be connected to the anode, so this will be an anode. I've got a little piece of insulating tubing right here that will prevent it from touching the cathode when it's hanging on the cathode side there. And then this is just the opposite. This is going to be a cathode, and I just made it by folding some more of that heavy gauge wire, and I put these cross pieces in just for a little extra surface area. And I got an insulating piece of rubber tubing on the side that would be resting on the anode, and this will wrap around the cathode side. One thing I'm a little concerned about is whether we're going to make good electrical connection. I think these will, because they're heavy, and this is probably going to be hanging on the anode side. I think it's probably going to be making good electrical contact. The cathodes are not particularly heavy right now. They will be after I plate a lot of copper on them, but right now they're not too heavy. So I don't know how good the electrical connection is going to be on the cathode side. I might have to put some kind of clamp on there to hold it in place. I also don't want an intermittent connection and sparking. So there's a close-up of the anodes and cathodes. So I got 3 of these and 4 of these in the cell. Okay, so got my nifty new scale out here. My old scale finally bit the dust, so I had to buy a new one. So let's weigh up the cathodes first. See what they weigh initially before we start plating copper out on them. Let's see here. Unit. So we're 154 grams. I don't know why it's beeping at me. I probably should have read the directions on this. So 154 grams on the cathodes, or 5.4 ounces. Okay. So that's what the cathodes weigh before we start plating anything. Why are you beeping at me? It's too new. I haven't had a chance to figure it out yet. So there's the anodes. 4 pounds, 1.9 ounces, or 1 kilogram, 868 grams. I hope that's showing up on the video, because I won't remember this. I'll need to get this off the video again. So okay, so we know our initial weights on everything. So let me put this back together, and then maybe we'll talk power supplies. Okay, for power supplies, I'm going to need something that supplies a fair amount of current. My little prototype cell was drawing about 3.5 amps at 2 volts. Now, the voltage across the cell may have been a little high. I've been doing some readings since then, and I think I had the voltage too high. I was getting a lot of dendritic growth on the cathodes, which I don't really want. So, yeah, the voltage was a little high, so I'm going to have to bring the voltage down a little bit. But I'm going to need a lot of current, because, you know, it's about 3.5 amps on that little cell. And that was 1 anode, 1 cathode. I got 4 anodes and 3 cathodes. So figure 3 cathodes, that's going to be about triple the current. So 3.5 times 3 is what, 10.5? So I need something that's going to be able to supply a fair amount of current at a really low voltage. So I've got this old Heathkit battery eliminator. I've had this for probably 20 some years. I think I bought it at a yard sale really cheap. It will put out an outrageous amount of current, about 25 amps or so. But it's only good for 6 or 12 volts. Well, between 6 and 12 volts. It's adjustable. The lowest it'll go is 6, the highest it'll go is 12. This one will actually get up to about 15. Let's see, it's been knocking around forever. I used to use it to run a hot wire foam cutter because it puts out so much current at a low voltage. It was great for that. Been sitting on my shelf forever. One of the feet were missing, so I just 3D printed a new one so it sits level again. So that will put out a lot of current. Voltage is too high though. So I downloaded the schematic of this thing off the internet. I was playing around with it a little bit. I thought, well, I can just take it apart. I can modify it and get lower voltage out of it. Then I had a brilliant idea. I'll just feed it with my variac over here and reduce the line voltage going into it. And then I don't have to get into this and tinker around with it. I can leave this original. I mean, hey, it's Heathkit. It's a classic. So, you know, it's a little beat up, but it's a classic. So don't want to mess with it. So I did some experiments with a dummy load. Did that off camera. So yeah, I can get about 10.5 amps out of this thing at really low voltage just by dialing back the line voltage going into it really low. So that's probably how I will initially try driving this cell. So I'll have to hook all this up. I don't want to run the cell indoors because it's going to produce gases and it's got corrosive liquids in it. So I want to run it outdoors. On the other hand, I don't want the power supplies outside, but I do have an area under my overhang here where I think I can put it where they'll be safe from rain and dew. So we'll have to set something up out here and see if we can make it work. At least, you know, test and see how it goes. I mean, this may not work at all. It's just an experiment, right? But I think it's going to work. I think we're gonna get some good clean copper out of it and some nice anode slimes to play with and extract precious metals from. That's what I'm hoping anyway. Okay, so I'm doing a little bit of a test here. I've got 2 gallons of water in here. And yeah, by the looks of it, it's going to take at least 2.5 gallons of electrolyte to get the liquid up to the level I want it. That's a lot of electrolyte. I've only got a little over a gallon of it made. So I'm thinking I need to put something in here to displace some of the water. So here's a couple bricks. Let me just pull this whole assembly out of here for now. There's one. They'll stay where I want them. That's another problem. I have to 3D print another doohickey to keep them where I want them, up against the sides, maybe. This back in. Yeah, see, they're in the way now. Okay. Alright, let's try this again with some skinnier bricks. I wonder. I think you can quite get 2 on each side, but maybe if I get another one, I could break it in half and get it in there. Yeah, that brings the level of the liquid up right about where I want it. Just below the tops of the anodes. Okay, what I've got going on over here is this container is full of copper nitrate solution that is a byproduct of my processing IC chips to recover their gold and silver. And it's been chilly lately, so I've moved it out into the sun, into a sunny area, so it can warm up. And I have put a couple of my ingots of cast copper in there, just so that any residual nitric acid in this stuff can dissolve the copper and get used up and concentrate the copper nitrate solution a little further. And you can see there's a little bit of activity, a little bit of bubbling going on in there. So the last little bit of nitric acid in that solution is getting used up. Couldn't tell you what the concentration on this stuff is. I will try to figure it out. I have a battery hydrometer coming, and maybe from the specific gravity I can figure out what the concentration is. But at least if I know what specific gravity I am working with, as long as I get that same specific gravity in the future, I should get the same results. I will probably leave this out here to stay warm the rest of the day, and maybe for the next couple of days, because I'm not quite ready to set up the cell yet and try it out. And just make sure all of the nitric acid in there is used up. Alright, here I am filtering the copper nitrate solution that's going to be the electrolyte in the electrolytic cell. So the solution's been hanging out in here for, I don't know, a week, better part of 2 weeks probably. I've got some copper bars down in there. Ooh, they're a little eaten up. They used up the excess nitric acid that was in the solution. So that reaction seems to have stopped. So I'm just going to filter it, get it good and clean, and set it aside until I'm ready to start up the cell. And between what's in here and what I've got somewhere else, I've probably got about 1.5 gallons of fairly strong copper nitrate solution, which I think will be enough to get the cell up and running. Okay, I would say everything is pretty much ready to go here. I have some extra anodes cast from my cement copper waste for when the anodes in here are worn down. And I found some skinny bricks at Lowe's to line the inside of the tub with to displace some liquid. So hopefully my 1.5 gallons roughly of copper nitrate solution will be enough to get this cell up and running. So all I really have left to do is get this thing set up and running and see what happens. So I'm going to start putting all the pieces together and we will give it a shot. Alright, I've got it all set up. I've just changed my mind. I've decided I am going to do it indoors. I'm going to try and keep the voltage across this cell low enough that there's no electrolysis going on, so we shouldn't be evolving hydrogen. I don't think we'll have much in the way of other fumes. And just because it's too darn wet and humid outside for the electronics, plus we've got a lot of semi-feral stray barn cats in the neighborhood. We're in a rural area, and they're always sticking their faces and paws in things, so, you know, I'm going to put it inside. I think this huge building I'm in, hello, I don't think that the fumes that are going to be evolved are going to be a big problem in this big building, so. And yes, I've got power in my workshop again, so that's a beautiful thing. So we're going to set it up inside. So I've got the variac over here. I've got the Heathkit battery eliminator power supply over here. All I have left to do is to fill the cell up with electrolyte, connect the wires up to the anode and cathode rails, and power it up and see what happens. So let me round up my electrolyte and get it going. Alright, let's get some electrolyte in this cell. So here's my roughly 1.5 gallons of copper nitrate solution, recovered from getting gold out of IC chips. I have a lot of videos on getting gold out of IC chips. In fact, these copper anodes are made with cement copper waste that came as a byproduct of getting the gold out of IC chips. So I've got lots of copper nitrate. Now, I am well aware, everybody, before you start, hammering on your keyboards, I am well aware that copper refining cells generally use copper sulfate as an electrolyte. Although copper nitrate is not unheard of. It is sometimes used. And copper nitrate is what I happen to have. It's actually kind of complicated to make copper sulfate. Sulfuric acid doesn't directly attack copper. So it can be a little complicated to make copper sulfate. Now I could convert this to copper sulfate, but I'm just going to use it as is. What the heck? Oh, that is just about the right amount of liquid, let me tell you. I'll give you a shot. It's coming up to just a little below the tops of the anodes. So the tops of the anodes are sticking out of the liquid, which is exactly what I want. Because I got brass screws in the tops of the anodes, I don't want them in the liquid. And I don't want the wires that are holding the anodes up in the liquid so that they'll rot away and the anodes will fall off. So this is perfect. Alright, I'll give you a close-up of this. The lighting in here isn't the greatest, but we're about, I don't know, 3/8, heavy quarter to 3/8 below the tops of most of the anodes. This one's sticking up a little higher, but I could bend the wire and push it down a little more. Okay, so yeah, that looks pretty good. The spacing between the anodes and the cathodes looks pretty good. Alright. One thing I was going to give you one thing I was going to do was show you the specific gravity of the liquid I'm working with. So let me find my hygrometer. Here it is. So here we go. It is right about 1.275. I don't know if that's showing up. Let me get a better focus. So is that good? I don't know. I guess we'll just have to try it and see. I'm thinking if the resistance of the cell is too low, what I can do is dilute it with some water. If the resistance of the cell is too high, I guess I'll have to turn the voltage up, which I don't really want to do. But yeah, those are really my only options at this point, because this is the specific gravity that my copper nitrate solution is. I guess I could evaporate it down if I have to. Okay, so the anodes are on this rail over here. So we'll hook that rail to the positive side. The cathodes are on this rail over here. So hook the negative to that side. Okay. I'm probably just going to want to fit the lid on loosely. Maybe, maybe not. I don't really want to have sparking going on in here with the lid on. We'll see. Alright, let me reposition the camera and we'll fire this thing up and see what kind of voltage and current we get across the cell. Alright, so here we go. Let's see what happens. I'm going to turn on the variac. I'm going to turn on the power supply. Now the variac is at 0% output right now, so you can't really see the variac. Let me back up a little bit. And I am going to ramp up the output on the variac. Now my goal here is to get about 10.5 amps of current through the cell if I can at the lowest possible voltage. I think the lowest, keeping the voltage across the cell as low as possible will ensure the best crystal growth on the cathodes and prevent electrolysis. So we don't want that. So let me slowly ramp up the voltage here. We're going to be a while before we see. Okay. Let me zoom in on the panel here on the battery eliminator. So we're about 2.5 amps. Yeah, the voltage level's pretty low. Let me continue ramping this up. See? Okay, so we're right about 10 and a... It's maxing out right about 10 amps. If I can turn the voltage back down, which I want to, because I don't want to have electrolysis. There's a point there where the voltage just drops off really, or the amperage drops off really quickly. I'm going to have to get a more sensitive voltmeter and see what the actual voltage across the cell is. Because this analog meter is just too coarse. Now I look inside the cell here. I don't see any bubbling. So if there's any electrolysis going on, it's got to be pretty minor, because I don't see any bubbling around the anodes or the cathodes. Okay, I'm just going to let this run for now and go get my better meter, and we'll get a better reading of what the voltage in the cell is. Then we can get off of this analog meter. Okay, I've got my meter. Let me plug it in here. Turn it on, and there you can see right around 2 volts is what we're pulling across the cell right now. Right about 2 volts. And the current has dropped to about 9 amps. I was hoping for about 10.5 amps, but I will take that. Let's see here. I just want to keep the voltage low enough we don't have electrolysis. So the variac's at only 30% output. And really adjusting the voltage adjustment on the battery eliminator doesn't do anything. So, alright. So I'm thinking the voltage is still a little high. Let me try turning it down a bit. Current's dropping off pretty quickly. Let me bring this back up close to 10 amps. And just below 2 volts on the cell voltage. It's not high enough to cause electrolysis, but I have read that voltage this high will cause bad dendritic growth on the cathodes. And it really should be lower. Ooh, speaking of growth on the cathodes, holy cow. Let me pull one out. Let me turn the power off so I don't cause a short circuit. Let me pull one out. Look at that. Holy cow, I hope that's showing up. We've got growth on there already. This thing's been running for all of maybe 10-15 minutes, tops. Alright, turn it back on. Okay, so I've been thinking about it. I'm thinking the only way that I could get the voltage across the cell any lower would be to concentrate the liquid in here more, so it's more conductive. And the only way I could do that right now is through evaporation, which will happen over time. So I was aiming for 10.5 amps at maybe, a little below 1 volt. I got 10 amps at not quite 2 volts. It's just going to have to be what it is, because I can't concentrate this liquid anymore. I suppose if I had some copper sulfate, I could dissolve it in there and increase the conductivity of the cell, but I'll tell you what, we'll just let it run as is and see what happens. If we get a lot of dendritic growth on the cathodes, I'll just pull them out from time to time and knock those dendrites off so we don't get a short circuit. I'll tell you what, the old Heathkit battery eliminator is getting a little warm. It hasn't run this hard in quite a while. It's got the smell of old electronics that's working hard. It's putting out 10 amps, but only at 2 volts. So it's not, what's that, 20 watts? That's not too bad. So the voltage kind of dances around a little bit, which is odd. I suppose maybe it could be due to bubbles on the anode or cathode. I don't know. Let me wrap it. Yeah. Give it a little bit of a wrap and the voltage goes down, which could be because bubbles are coming off, although I didn't see any rising. Huh, interesting. I still don't see any bubbling anywhere in here. Alright, I guess we're just going to let it run. Let me loosely put this lid on just so no debris falls into it. And we'll let it run for an hour or two. Wow, the voltage has dropped way down. Current is pretty much holding steady at 10 amps. So at 10 amps we should move a lot of copper from the anodes to the cathodes in a fairly short time, I'm thinking. It's just 15-20 minutes. I could see that there was already copper plating out on the cathodes. I'm thinking after a day or two it's going to be pretty substantial. So I'm just going to let it run for now and see how it looks. Okay, it's only been a few minutes since the last segment, and I had a thought. I need to protect this from short circuit in case the dendrites do grow across from anode to cathode and short things out, or in case, you know, I'm messing around in here and I cause a short circuit, which I should do is just turn off the power before I mess around inside. But what I'm going to do is I'm going to put an inline fuse. So we're running pretty steady at 10 amps. I've got a 12 amp slow blow fuse in here. So we'll just put that in line and start her back up and let it go. So if something should happen, we'll blow that fuse rather than blow up the power supply or start a fire or anything. So that would be a good thing. Now I'm not expecting the current through the cell to rise over time. If anything, I'm expecting it to decrease over time. As the anodes get chewed up, they'll have less surface area and the current through the cell should drop. So not rise. The only way the current's going to rise through the cell is if the conductivity of the fluid changes during this process, which is possible. I'll have to keep an eye on that. Or if there's a short circuit. So, but we are running steady between 9.5 and 10 amps, I'd say. And I'm just going to let it run. I'll give you another look at it towards the end of the day, and we'll see how much copper we have moved from the anodes to the cathodes. Well, the cell's been running for a while. Oh, I think I said I put a slow blow fuse in it. It's actually a fast acting fuse. I think I misspoke on that. I didn't go back and listen to what I recorded, but I think I misspoke. So it's a 12 amp fast acting fuse. So just in case there's a short circuit, it'll blow quickly. Anyway, we've been running for a while. The voltage kind of all over the place. It'll dip down into the low 70s and then up into the upper 90s, and just I'm not sure why. I mean, I thought maybe it was bubbles, but I don't know. It's kind of odd. But lower voltage, as far as I'm concerned, is good as long as we're still getting close to 10 amps. So, yeah, if the voltage keeps drooping too much, if the amperage starts dropping off, I can always crank the variac up a little bit because it's only at 30% output over there. So we can pump a lot more juice into this thing if we need to. See, the voltage is heading down, but it'll go right back up again for no good reason that I can understand. Otherwise, things seem happy enough. So I'm just going to let it run. It's getting late in the afternoon, but I'll let it run at least until dinner time. I don't know if I want to let it run all night since it's brand new. I need to get a little experience with it. I may turn it off before going to bed and then turn it on again tomorrow morning when I can kind of monitor it. We'll see. Okay, this has been running for a little over an hour. The heat kit battery eliminator is a little warm but not really hot. The voltage bouncing around gets up close to 2 volts and then down into the 1.7s. Not sure why it's bouncing around so much. So we're putting just short of 10 amps at almost 2 volts into this cell. So that's about 20 watts. So I would expect it to start getting warm after a while, but it still feels about room temperature. Anyway, since it's been running for a little over an hour, I'm going to stop it and pull out some of the anodes, and we'll have a look at them close up and see how they look. Alright, I've pulled out all three cathodes for inspection, and they've all got the same issue. They're growing dendrites from the edges right here and on the bottoms. Well, that one on the bottom anyway. So yeah, this is what I was afraid would happen if I was running the cell at that high a voltage. So I can't make the cell more conductive easily. So what I'm probably going to have to do is just ramp the voltage going into the cell down. That's going to drop the current. So we're not going to get as much copper moving as maybe I'd like. But at least we won't get these dendrites growing. It's going to eventually short out the cell. Hopefully. Hopefully we'll get a nice smooth layer of copper on here. I mean, there is copper plating out on here. It's all over the place. It's not just on the dendrites at the corners and edges. It's all over. And for only an hour running, that's probably not too bad. But yeah, this is just this is going to short out the cell in pretty short order if I let those continue to grow. So I'm going to have to back the voltage down and reduce the current. And then I will think about ways to reduce the resistance of the cell. I don't have any more copper nitrate to put in it, but maybe copper sulfate, adding some copper sulfate to it, which I might have some. I will have to look around. I might have some copper sulfate in amongst all my chemicals, and we'll see. And maybe adding some copper sulfate to the cell will reduce its resistance and allow more current to flow at a lower voltage. So let me put this back together and we'll see if I can get it running again at a lower voltage, but no doubt lower current too. Alright, I've got the power back on. We're pretty much right where we were before. So I'm going to decrease the voltage over here at the variac. Alright, so we're a little below 1 volt now. We're only moving about 4 amps. We've only got about 4 amps of current flowing. Actually, let me turn it back up because the voltage is just continuing to droop. Turn it back up some. Okay. We're right about 4 amps. We're below 1 volt across the cell. Well, the voltage is going to bounce around again like it did before. It may pop above 1 volt. I'm not too worried about it. I think the voltage is still a little too high, but the dendrites should not grow anywhere near as fast now with this lower amount of current flowing. So I'm just going to let this sit for the next few hours and see how it looks. I'll probably shut it down sometime after dinner time. A little leery about letting this run all night since it's so new and I don't know how it's all going to work. So I'll check on it periodically and probably, like I said, shut it down before dinner time or before I go to bed, and then we'll come out and look at it in the morning and probably start it up again. The current slowly rising a little bit. I'm going to have to keep an eye on this. Voltage and current, they're kind of dancing around. Okay, it's the next morning, so this has just sat off all night long. I just didn't trust it to run without me checking on it from time to time. I may learn to trust it a little bit. But I did a lot of thinking overnight about this thing. Really, the only way I can get the current up while keeping the voltage down is to reduce the resistance of the cell. So we were getting about 9 amps at just under 9.5 amps at just under 2 volts across this cell. So that gives me a resistance of about 0.222 ad infinitum ohms, 0.22. So that's actually pretty low resistance. But maybe I can make it even lower. If I were to increase the amount of copper nitrate dissolved in the electrolyte, that might bring the resistance down even more. Unfortunately, I don't have any more copper nitrate. What I do have, I looked around in my bag of tricks, I have some copper sulfate. Now, I didn't think I had this much. This would almost be enough to run the cell on right here. I thought I just had a little bit. But what I can try doing is putting a little bit of copper sulfate in the cell, and as this dissolves, hopefully that will bring the cell resistance down even lower. And then I can run at higher currents at the low voltage, under 1 volt that I want to run at. So I'll give it a try anyway. I had nothing to lose. So I begin to see the advantage of using copper sulfate in these cells over copper nitrate, because you can adjust the resistance of the cell really easy. If the resistance is too high, you can just add a little bit of sulfuric acid to it and that'll bring it down. If the resistance is too low, you can just dilute it with a little water and that'll bring it up. I can't do that with this. I can't add sulfuric acid to it because it's going to produce free nitric acid, which is going to eat up everything in there and release noxious gases. So I don't want to do that. So yeah, I see the advantage of copper sulfate now. But of course, the advantage of the copper nitrate is it was free. So that's a pretty big advantage in itself. So let me get a little bit of this in here. Now, it is chilly this morning. It's quite cold. This is sat overnight. So what I'm thinking is I can put some of these copper nitrate or copper sulfate crystals in here, and it's just going to take them a while to dissolve. They'll probably just sit down there on the bottom and slowly dissolve. Probably as the day warms up. I could throw an immersion heater in here and warm the liquid up. That's a possibility too. But we'll just try spooning some of this in and see what happens. I'm going to put a fair amount in. A highly scientific measurement of, what's that, about 4 teaspoons full so far? We'll make it 6. And see if there's any difference in the way the cell operates as the day goes on. And this stuff goes into solution. Okay, let me get ready to fire this thing up again. Okay, let's get this cell fired up now that I've got the copper sulfate in. In fact, you know what? There's enough copper sulfate here, maybe, that if I can't get the cell working the way I want it to with the copper nitrate, I might just dump this electrolyte out, make up some new with copper sulfate, distilled water, and sulfuric acid, and try again. We'll see. We'll see. All right, on with the variac. Turn on voltmeter. On with that. And we got a little over 1 volt across the cell. And it's only pulling about 2.5 amps right now, which is a little odd because we were getting more like closer to 5 amps at 1 volt yesterday. So that's kind of odd. So I may just let it sit here and see what happens. I wonder if there's a sensitivity to temperature. It is quite chilly this morning. Yeah, it's quite chilly. So, yeah, maybe the current will go up as it warms up. We'll see. I don't think I'm going to mess with it right now. I think I'm just going to let it run and see what happens for a bit while I work on some other stuff. Just sort of check it from time to time. Okay, it's about mid-afternoon, so this has basically been running all day, and I guess the copper sulfate crystals I put in it had essentially zero effect. The resistance of the cell hasn't dropped any. We're still running just under a volt at, I don't know, 3.5 amps maybe. So, yeah, not as many amps as I would like, but at this low voltage, we're not going to be doing any kind of electrolysis in here. So I'm not going to be wasting power converting the liquid to hydrogen and oxygen and, making a potentially explosive gas, so that's good. And I tell you what, I pulled out a couple of the cathodes around lunchtime and looked at them. And the copper plating is a lot smoother, and we're not getting the dendrites growing off of the ends like we were. They're actually getting plated over with more gold and rounded over. So I'm going to let this go for a while longer, and maybe before dinner time, when I'm ready to shut this down for the night, or actually I might leave it on all night, since at 3.5 amps, we're not moving much copper. I don't think there's going to be much chance of a short circuit here. I may leave it on all night. But I'll give you a look at a couple of the cathodes before the end of the day, when it gets too dark to see. Alright, it's not really that late in the afternoon, but I'm going to have to leave soon, and I probably won't be back till long after dark. So I just thought I'd give you a look at the cathodes before I have to leave, and show you what's going on here. So we've obviously got some good copper deposition on here, and the really pointy sharp dendrites that were on the ends are kind of have rounded knobs on them now, so they're not continuing to spike outwards. So that's kind of a feature of all of them here. That seems to be happening. It's weird that they're growing outwards from the pointy ends rather than towards the anodes, but I think that's just the charge is concentrated at the pointy areas, which is why that's happening. So yeah, so even at 3 amps, a little over 3 amps of current, we're getting some copper deposited on here. So I think I'm just going to put these back in and let it run, and I may get brave enough to let it run all night. The power supplies are only slightly warm at 3 amps. The copper is growing very slowly. I've got the fuse in place in case something shorts out. So I think I will go ahead and probably let it run all night. So let me get it put back together and get it started up again, and let it go. Alright, it is the next day. In fact, it is afternoon of the next day, and this has been running the whole time at the lower current, lower voltage level. I had a scrap pickup I needed to do early this morning, and my truck is just absolutely stuffed to the gills with computers, laptops, printers, all kinds of stuff. I've got to spend the afternoon unloading it and finding homes for all that stuff till I can scrap it out. Got scrap iron too, motors. So I'll put a link up in the upper right corner to the video I'm making about this scrap pickup, because that'll be done before this video is done. But this has been running. I had a quick look at a couple of the cathodes this morning, and really a surprising amount of copper has been transferred over to the cathodes, even though we're running at like 1/3 of the current that I was targeting running at with this thing. So I'm pretty happy about the amount of copper that's come over, although remember, the copper is not the point of this. The getting the anode slimes out of those ingots I cast is the point of it. And, well, that's happening too. Let me shut this thing down. And we'll take a look at a couple things here. I'll pull a couple of the cathodes out, and we'll take a look at them. And we'll take a look here. Here's one of the anodes. See this black stuff on here? That's anode slimes. That's what I'm trying to get, and we are getting a fair amount of it. It is coming off pretty good as these anodes dissolve. So that's pretty good. So let me pull the cathodes out and we'll take a quick look at them. So here's the cathodes. And yeah, look, there is really a huge amount of copper growth on there. I was not expecting to see this much copper growth in only like a day and a half with, you know, 3.5 to maybe 4 amps of current going through the cell most of the time. So really, we're moving a lot of copper. And it's not taking nearly as long as I was afraid it would. I'm thinking at this rate, you know, it may just take a week or so to dissolve away those anodes. I don't know. So it's possible. So I'm pretty happy with the way it's going. I think I'm going to stop tinkering with it and just let it run for now. And use up these anodes and collect the anode slimes. And then I have some ideas for further tinkering once I start the cell up again with a new set of anodes. And one of my ideas is, I was thinking there's a couple of possibilities about why I can't get the current up to where I want it without the voltage spiking. And there's a couple of problems. The internal voltage of the cell, or the internal resistance of the cell, is not just limited by the conductivity of the electrolyte. There's also the area of the electrodes. So these cathodes may not have as much area as they should. So I think I'm going to make a new set of cathodes for when I restart the cell that will have a larger area. And also, there's probably resistance at the point where the anodes and cathodes hang over the rails because there's a really small contact area. So it's possible that we're just not getting, you know, a really good contact there, and there's some resistance at that point. So I will work on ways to improve that as well for the next batch of anodes and cathodes that go into this cell. But for now, I think I'm just going to put everything back together and let it run. And we'll see what we get, how long it takes to dissolve away the anodes, and whether or not I have to replace the cathodes because they get so full of copper. I may have to shift them around. This one here really is getting fatter than the others are. So I may have to like play musical chairs with them so they all get equally coated. I may need to move around the anodes too so they all dissolve at an equal rate. We'll see. But wow, we're moving a lot of copper in a fairly short period of time. I'm pretty happy with how this is working. So let me get it back together and get it up and running again. Okay, so here we go. The cathodes are going back in. And we're going to restart. Everything's off right now so I don't cause an inadvertent short circuit while I'm playing around here. So I'm just going to let it run, and we'll see how long it takes to dissolve those anodes. So I think that's going to be the end of this video. Got the cell up and running. It's working better than I expected, even at the low current that it's running at and the low voltage. So I'm just going to let it run, and in the next video, once those anodes are all dissolved, we'll look at collecting the anode slimes and processing them and setting the cell up to run again, probably with a few modifications. Larger area on the cathodes, and maybe a better way of more electrically secure way of connecting the anodes and cathodes to the voltage rails. So we'll look at that and see if cell 2.0 works even better than cell 1.0. Alright, well, thanks for watching. I hope you found this video entertaining, educational, inspirational, killed some time, whatever. Give the video a thumbs up, give it a like, and subscribe to see the future videos, because there will be video coming where we get this anode slimes and try to pull some gold and other precious metals out of it. And of course, we'll be talking about cell 2.0 in those future videos, and lots of other videos too. So subscribe to see those videos when they come out, and press the little bell icon YouTube makes you press to be notified when the videos come out. And thanks a lot for watching. Have a good day. I'll see you in the next video. Bye.